Hello everyone, and welcome to another video. Today I'd like to talk about expressing vectors in different frames, as well as how to translate from one frame to another using rotation matrices. As we delve deeper into our study of kinematics and dynamics, we're going to see that often it's really convenient to have multiple coordinate frames, and we're going to need tools and notation to be able to write down and express a vector in any arbitrary frame. As you know, I like to use examples to motivate our discussions, and I also like to fly unmanned aircraft. So let's see if there's a way that we can combine the two of these. So if this sounds like more fun to you than a tour of Willy Wonka's chocolate factory, I guess the kind where nobody meets their gruesome fate, then let's get this in the air.
In this scenario, let's consider a situation where all I want to do is describe a vector. So let's use this jar to denote the start of the vector, and that star to denote the end of the vector. What we can now do is use this red rope here to connect the start of the vector to the end of the vector, and maybe let's call this red line the vector P. Now that we see this vector P, the next thing we'd like to do is ask someone to describe this vector P. So in this case, we're going to ask this guy named Fred. So I'm putting on this hat with the label Fred so you can see it from his perspective. So we're really asking Fred to describe how to go from the base of the vector to the tip. So this requires Fred to attach a coordinate system so he can specify the x-axis there and the y-axis there. And in this situation, I guess the z-axis goes into the page. So what Fred can do now is he can measure how far does he have to walk along his x-axis, and how far along does he need to walk in his y-axis to go from the base to the tip. And he says, oh, you need to go 1.88 meters in the x and negative 0.68 meters in the y. Now, let's repeat this, but ask a different observer. So this observer, let's call him Joe. So I'm going to switch hats. So I have this green hat with a new label that says Joe, and Joe is going to use a slightly different coordinate system here. So it has the same z-axis as you see here, but it's aligned slightly differently. Now, we can again have Joe put down what he thinks is an x-axis there, and what he thinks is a y-axis there, and like we said, they share z-axis with both Joe and Fred. Now, we ask Joe here to make the same measurement, namely, how do you go from the base to the tip? So he measures how far do I need to go in my x-axis, and how far do I need to go in my y-axis? And he says, oh, you know what? You just need to walk 2 meters in the x-axis and 0 meters in the y. So something is clearly inconsistent. This is the exact same red vector here, but they don't appear to be numerically the same.
Okay, so we see here that the thing that's lacking here is actually our notation here. Because clearly we saw that this vector from Fred's perspective, right, positive 1.88 and minus 0.68, this is clearly not equal to what Joe saw here, right? So here was Fred and here was Joe. So what would be better here is we apparently need to adopt some notation where we can discuss having a vector, which we called P here, and we're going to now need to denote which frame am I trying to express this in using numeric values. So we're going to adopt a right superscript here. So I'm just going to use R here for an example here. So what this right superscript R means is this is going to be the vector P, but it's numerically expressed in FRs. I guess numerically expressed in FR is maybe a better way to put this here, right? So the values, the first value in here is going to be the how far you go along the X value in frame FR. The second value is going to be how far you go along the Y value of frame R here. So in this case, to make this a little bit less ambiguous, right, we really should have written here that this vector P from Fred's perspective here is 1.88 and minus 0.68. And the vector P from Joe's perspective is 2.0 and 0 here. Okay? So this will clear up a little bit of some of this ambiguity here. So again, let's use this right superscript to denote which frame of a given vector is expressed in numerically here, right? Okay, so now that we've got this down, the next thing that we should maybe talk about here is clearly there's some relationship between, I mean, both of these are talking about the exact same vector. It's just from a different perspective here, right? So there must be some way to translate between Joe's reference frame and Fred's reference frame here. So this leads to a discussion here now of rotation matrices here. So let's talk about rotation matrices. Okay, let me erase some of this board here so we get a little bit more space here. Okay, so what we're talking about here is we need the mathematics here to be able to translate a vector that's expressed in one frame to it being expressed in another frame here. So let's again consider that same vector, let's call it P here, but maybe let's write this in 3 dimensions here. So I'm going to try to draw this now, and let's draw a coordinate frame in 3 dimensions here. So let's do it like this here. So here's the x hat r, here's y hat r, and then the right-handed coordinate system is something like this. So here's z hat r. So here is frame fr here, right? So all of these are right angles. So here's a right angle here, here's a right angle here, and the last right angle is kind of like this. I think everyone gets the picture, hopefully, right? So this is my right-handed coordinate system of x, y, and z going down here, right? So what I'd like to do now is, again, let's consider a vector p here. And I'm just going to draw it like such, and then we'll try to decompose it in just a second here. So here's this vector. Let's call this vector p. I'll put a bar here so we can denote that. And let's see if we can make this slightly understandable here. So I'm going to project this vector up here into the xy plane here. So there's going to be some component like this and like this. So you can think about this, I guess, if you wanted to project this red vector into this plane, right, it would have some kind of a footprint like this, right? You can kind of see what that's looking like here. And then finally, let's also project the z component of it onto this z-axis. So let me see. So graphically, that's gonna, I guess it's gonna be parallel to sort of, well, no, actually, no, sorry, it's gonna be parallel to this line here, right? This line. So it's gonna go back like this. Okay. Okay, so let me now pick up a different color here, because what I'd like to show here, so I know this is a little bit confusing, but again, think about this here. This vector p, it's just a vector in 3 space, and now I've attached some coordinate frame fr to this thing here, right? So why I wanted to project it on all of these axes x, y, and z here is so I can draw, let's try to draw this in green here, maybe like a vector here. Let's call this vector a. And then I'm going to draw a vector b, which goes along the y-axis here, like this. Let's call this vector b. And then finally, a vector that goes along the z-axis like this. And let's call this vector c. Okay? So that's the picture that goes along with this here. The reason I'd like to do it like this here is because now we can write from a vector mechanics perspective here that this vector p that I'm interested in, right? It's just the vector addition of a plus b plus c here, right? So I think you wouldn't argue with this, a plus b plus c. And notice right now I don't have any right superscripts here, so I'm not actually trying to express this vector in this coordinate frame yet. I'm just saying from a vector addition perspective, you just have these vectors a plus b plus c. If you add them tip to tail, you'll end up with the vector p here, right? Okay, now this thing is going to get a little bit ugly, so tell you what, let's just draw this in only the xy viewpoint, right? Let's just draw it in the xy plane. So let's redraw in the x hat r, y hat r plane. Okay, so again, to copy that diagram here, so what we're going to end up with here is let's draw this here. So I got x, whoops, let me try, I want this to be straight up and vertical, so let me try not to be sloppy here. So here is my x hat r, and then I've got, maybe let's make this a little bit bigger because this is actually going to take up some space here and be important in a second here. Okay, so here's y hat r. Okay, and then let's draw the vector p. It's going to look a little bit something like this here, right? So we're going to have a p. Here's my red vector p here. And now I guess here, if I want to draw some of these dashed lines here, right? So here's a dashed line that comes like this. Here's a dashed line that goes like this here. right? And then I can draw the vector A, which was basically the projection of this vector onto this x-axis here, right? So here's my vector A. Okay, here's vector A. And then here's vector B down here. And vector C is going into the page here, right? So here's, well, I guess, yeah, C is like that here. And I guess we should also write that Z hat R is going into the page here, right? Okay. Great, okay. Okay, so again, this is the same picture here, but it's just looking at in the xy plane here, okay? So you can think about this vector P, it's tilted into the board here, right? It has some component along the z hat r direction, right? So it's going down here, but obviously I can't draw this in a two-dimensional view. So what I want to do now here is, let's go ahead and say that this distance here, right, the length of this vector A here along the x hat r direction, let's call this thing alpha here. So I'm going to draw it like this just to show like this distance here, right? Let's call this alpha units here, right? Let's now call it beta units of is the length of the vector B here, right? So this length here, let's draw it like this in blue here. This is going to be beta units. Okay, and then similarly, the length of the C vector, I guess I can't really draw it here, but let's call this thing gamma units. So you got alpha, beta, gamma here, right? That's the numerical values here, or the lengths of these vectors, okay? So the reason I want to do that here is because now what we can do is, let's consider expressing P in FR, okay? So in other words, what I wanted right here is I want to say P in R, right? That's, well, we said this is A plus B plus C here. But if I want to add these things numerically, they all have to be in the same coordinate frame, right? So I need to put superscript R's on all of these, right? So if I want to add them all together and make the numerical values match here, they all better be in the exact same coordinate system here, right? Okay, so let's think about this here, okay? What is this thing here? So let's look at each vector, each component one at a time. A in R here. So this is the vector A expressed in frame R. So what we're trying to do here is I need three numbers here. The first number tells you, if I want to describe this vector A, how far do I go in x hat R's direction? Then how far do I go in x hat Y's direction? And then how far, sorry. Maybe, sorry, let me write this down. This is the x hat R component, right? This is the Y hat R component, and this is the Z hat R component here, right? So this first numerical value is, how far do I walk in the XR direction, X hat R direction? Well, we just said right here, you walk alpha units in that direction here. How far do you go in the Y direction? Well, lucky for us, it's 0, and it's 0 down here as well, right? Okay, great. So here's how you would express this vector A in the frame FR component, right? Let's do the same thing for BR. So BR, right? It's the exact same thing. The vector B here expressed in frame R means how far do you walk in X, how far do you walk in Y, and how far do you walk in Z? Well, just from the geometry of the picture, I think you'll agree that this is 0, beta, 0, right? And similarly for C in R, this is going to be 0, 0, gamma, right? So let's just put that in here for the left-hand side here, right? So I basically just have alpha 0, 0 plus 0, beta 0 plus 0, 0, gamma, right? So at the end of the day, what we end up with here is alpha, beta, gamma. This is how you get, or how you would describe this red vector P if you wanted to describe it numerically using frame FR here, right? It says you go alpha units in X hat R, then you walk beta units in Y hat R, and then you walk gamma units in Z hat R, and that will get you from the base of the vector to the tip of the vector here, right? Okay, that's great here. So let's box this up and save it here. Maybe let's, maybe what we should do here is, let's move this over here. This is going to be actually a little bit useful later here. So let's write down our result here. So P in R is going to be alpha, beta, gamma. Okay, so let's save that here, and then let's erase the rest of the board here. Well, not the rest of the board. I want to erase these calculations here. And now what I want to do is let's consider now a second frame here. Okay, so instead of this frame R here, let's now consider another frame here. Let's call this frame F1, how about? Okay, so frame F1 here is obtained by rotating FR through right-handed angle psi about the z hat r, which is also going to be the z hat 1 axis. So what that means here is I want to take this picture here, the black lines here, right, which represent my reference frame, and I'm going to rotate it about the z-axis, which is, in a right-handed sense, it's through the board. So this whole thing is going to tilt here, all right? So maybe let me just draw it instead of me talking about it here. So let me just draw this here. So this now, so this x-axis, right, is just going to rotate through angle. This is positive psi. Right? And this now becomes x hat 1, right? This is the x-axis of frame 1 here, right? Similarly, the y-axis here is going to rotate through that same angle here, right? So down here, here is positive psi, right? And now this becomes y hat 1, right? And I guess the z hats stay the same, right? These two are common here because all we've done is we've rotated about the z-axis here, right? So now I've got this new frame called F1 here, right? And we can ask ourselves the exact same question now is, this vector P hasn't changed, right? It's the exact same vector, but now I want to express it in frame 1 instead of frame R here, right? So in this case, what I'd like to do here is I want to express P in F1 here, right? So in other words, I want to have this vector P here, which earlier we said P was A plus B plus C here, right? But now I want to express this in frame 1 here, right? So again, in order to make the left-hand side numerically equal to the right-hand side, I got to put 1 superscript on all of these other components here, right? Because what I want is, I want to now describe all of these from the 1 perspective here, right? Okay, so the question now becomes, just like we did earlier here, what is A1, right? So it's question mark, question mark, question mark. There's 3 numbers I got to stick in here. Again, what the first number here in this vector means, it's the component now of how far do you have to walk along x hat 1's axis, right? The second component is how far do you have to walk along y hat 1's axis, and the third component is how far do you have to walk along z hat 1's axis in order to go from the base of the vector to the tip of the vector here, right? So this is the 3 numbers that we need to compute here, right? Okay, so if you think about this long enough, let's think about this. A here, where is the vector A? It's this green line here, right? So I got to ask myself, how do from the origin here, or the base of this green line here, to get to the tip of this here, but I want to describe that in the 1 frame here, right? So you can actually draw a couple of right triangles in this picture here. So maybe let's do this in blue here. So I'm going to have a right angle coming off like such here. So this here is a right angle, right? And then similarly down here, I got another right angle here, like this. So if you look at this thing long enough, right? So again, I'm trying to describe, let's just focus on A. I just want to get to this tip right up here, okay? So you see, actually there's a hypotenuse of this right triangle here with hypotenuse alpha here, right? So I think everyone would agree that this distance here, isn't this just going to be alpha cosine psi, right? And then this distance here is alpha sine psi. Would everyone agree, right? So coming back to our question over here of how do I go from the base of this A vector to the tip of the A vector? Well, first off, I got to ask, how many units do I walk along the x hat 1 axis here, right? So if you look at this, well, you have to walk apparently alpha cosine psi units in that direction. Let me make this a little bit bigger so I have a little bit more space. Sorry. Let's do this. All right, okay, so the first one, I walk alpha, cosine, psi units in the x hat 1 direction. That brings me to here. Now, the only thing I got to be a little bit careful of is how far do I walk now in the y hat 1 direction? I walk this distance here, that's the magnitude, but notice I'm actually walking, you have to go in the opposite of the y hat 1 direction here. So this is actually minus alpha sine psi. Again, pay real close attention to this minus sign. I guarantee you the #1 place people screw things up in rotation matrices is this minus sign that shows up here with this sign. And this is exactly where the minus sign comes from, right? Is I'm here, and now instead of walking in the positive y direction here, I got to walk in the negative y direction to get to the tip here, right? And then how far do I walk in the z direction? Well, that's 0, right, for this component. Right? Okay, great. So I think we nailed this thing for A1 here. Let's also do this now for what is B1 here, right? So again, B1, it asks us, how far do I walk in to get here? Now I'm talking about the vector B, this green line here, right? This horizontal green line. I got to figure out how far do I walk in the x direction? How far do I walk in the y1 direction? So, okay, so again, let's look at this triangle here. Again, it's a right triangle here. This right triangle now has a hypotenuse of beta here, right? So I think everyone would agree that this distance down here, this is beta cosine psi, right? And this distance here is beta sine psi. Right? Okay, so let's do it here. So how far do I go in the x1 direction here to get to this tip? Well, I go this direction, right? So here's from here up to here, right? So I go beta sine psi in that direction, right? And then how far do I go in the y direction here, the y1 here? So that is this distance, right? I go beta cosine psi, right? And then I go 0 down here. Perfect. And then lastly, I think the C component is actually pretty easy. C1 here, because the C component didn't change, right? The z-axis here didn't change, so C is actually pretty darn simple, right? This is just going to be 0, 0, and gamma. All right? Great. Okay, so let's just plug these 3 expressions in here for the right-hand side here. So if you write this down here, you end up with, well, let me see, you get alpha cosine psi plus beta sine psi, and then minus alpha sine psi plus beta cosine psi, and then you get gamma down here, right? Okay, great. You know what? Let's pull out alpha, beta, and gamma. In other words, what I could do is we can rewrite this whole thing in a matrix form here of something that looks like, I'm going to pull off alpha, beta, and gamma over here. And now what this matrix looks like, it's this 3 by 3 here where I got what? I got cosine psi, and then we got sine psi, and then a 0, and then you got minus sine psi, cosine psi, 0, and then a 0, 0, 1 here, right? And again, what's the left-hand side? The left-hand side is this up here, right? This is the vector p expressed in the 1 frame here, right? Now, what is this vector over here, alpha, beta, gamma here, right? Well, that's what we boxed up and saved earlier here, right? So if you look at this alpha, beta, gamma, that's the vector p expressed in r here, right? So this whole thing over here, this vector here, this is p expressed in r. And what this matrix here, this 3 by 3 matrix here, this is referred to as your rotation matrix. Because it's a matrix, if you look at this, the interpretation long enough, right, this matrix is going to allow you to take a vector that's expressed in frame R, and it will do something, and basically it will output the vector expressed in frame 1 here, right? So let's write that down here. Maybe I think we're done with this picture, so I think we can get rid of this. So at the end of the day, what we end up with here is we can write here the vector p expressed in frame 1 here is going to be this 3 by 3 rotation matrix, which a lot of times is denoted with a C here. This C here is a function of psi here, and there's going to be a couple of subscripts down here, so give me a second here. And this thing gets multiplied by the vector p expressed in frame R here, right? So this is a rotation matrix which we see goes from frame R to frame 1 here. So the notation that we're going to use here is a subscript where it's something like this, R, or something like this here, right? C1 with respect to R is a function of psi times the vector here expressed in frame R here, right? So in this case here, C1R psi here, this is a rotation matrix. This is also sometimes you might hear this called a direction cosine matrix, direction cosines matrix, or a DCM, right? But this rotation matrix goes from FR to frame F1 here, right? So again, we got to be a little bit careful here. Again, probably the second most common place that people will mix this up here is they'll either flip-flop these indices here, and they won't keep track of this rotation matrix. Does it go from frame 1 to frame R, or does it go from frame R to frame 1, or vice versa here, right? So the way we're going to keep this straight here is, if you notice here, the direction cosine matrix or the rotation matrix, it always is sort of multiplied on the left of the vector here. And now our notation here is going to save us, because we notice here that the way we're going to keep this straight here is this subscript, which is kind of closer to the right, it has to sort of match this subscript here, right? So these sub/super scripts should match, right? That will tell you that, okay, this rotation matrix is expecting to be multiplied here right next to something in frame R, right? So this R matches with this R, and the result is going to kick out some of that exact same vector, but now expressed in the one frame here, right? Or the other frame. So these two indices, or these sub and superscripts, should match, right? Okay, so this is our rotation matrix, and again, I guess maybe we should write this exactly down here, right? So this rotation matrix, again, it's a 3x3 here, right? Right, where it looks like cosine of psi, sine psi 0, minus sine psi, cosine psi 0, and then a 0, 0, 1 here, right? Great. So this is our rotation matrix. It has tons of special properties. It's really, really helpful. Let's talk about a couple of these interesting properties here. So first off, I think we're all, did I want to erase that picture? Yeah, I think we can erase this picture here. You guys all have it hopefully in your notes, or you can just rewind the video here to get this diagram again. So no biggie. Okay, but a couple of the interesting properties here. So rotation matrices are orthogonal. So if you remember, what that basically meant is every single row and column here, not only are they linearly independent here, but every row and column are normal to every other row and column here. So what's special about an orthogonal matrix here is, one of the consequences here of an orthogonal matrix here is that basically the inverse is just the transpose here. So this is rotation matrices are orthogonal, therefore the inverse is simply the transpose. So this is really, really helpful. So for example here, you know, we had this thing C1 with respect to R of psi here, right? If I wanted to calculate its inverse here, right, that is actually, there's no point in doing a full-on 3x3 inverse and paying all that computational power to do the determinant and do all this kind of stuff here. Instead, you just take this matrix and just switch the rows and the columns here, right? And if you think about this long enough, let's come up here to this notation here. If you look at what this is doing here, right? So you said we had this rotation matrix C1R of psi here times PR here, right? What if I want to take left multiply both sides by the inverse here, right? So in other words, I could turn this thing into C1R psi inverse P1 is equal to PR. Whatever would agree, that's the exact same thing. And now we said that, all right, this is great here. This inverse is the same thing as the transpose, so I could just switch this with the transpose, right? Now, if you think about what this is doing here, what is this matrix here? This whole thing. Maybe I should circle this whole thing, right? This whole thing, C1R psi transpose here. This is now some other rotation matrix, let's call it C here, right? Which takes a vector expressed in frame 1 and turns it into a vector expressed in frame R here, right? So in other words, this thing is C1, I guess R/1, like that, right? Times P1 is equal to PR. Right? So again, this index matches with this index, and then this index will tell you what the result is here, right? So this is really, really cool here. So we basically see that, okay, the transpose or the inverse of a rotation matrix, it's basically the same thing as flipping the order of the indices here. So you could write this thing as CR1 of psi, right? So here's a nice property here of these rotation matrices. So first off, never ever bother throwing, calculating a full-on inverse. You're just wasting computational power. Just take the transpose. And again, what that physically is doing here is it's just flipping the indices of the rotation matrix. So physically, you get another rotation matrix where all it's going to do is take you from the frame back to the original frame, right? Or vice versa. I'll let you guys figure that out, right? You can see clearly what's going on here, right? So that's super cool here, right? Okay, what else is really interesting about these rotation matrices? Well, if you remember, does everyone remember what an eigenvalue of a matrix did here, right? So let's consider, how about eigenvalues of this C, let's use our perspective, C1R of psi here, right? This rotation matrix that we cooked up, right? If you remember, right, eigenvalues were, they gave you an idea of sort of the maximum amplification or attenuation that a matrix is going to do. If you had something like y is equal to ax, right, the eigenvalues of A are going to tell you how much could this matrix A amplify or stretch or shrink this vector x in order to get a vector y here, right? Now, if you think about this rotation matrix, what if A was a rotation matrix? Physically, we see that this thing should not be stretching or shrinking that vector at all, right? Because what we did is all this is doing is it's changing the perspective of how we express that exact same vector here, right? So what we better, well, it better be true, and we hope that the eigenvalues of this rotation matrix, or in fact for any rotation matrix, right, their magnitude better be 1 exactly, right? Because that's going to basically say that no matter what vector you put in it and you transform using this rotation matrix, it will not stretch or shrink that matrix, that vector here, right? So if you want to go over to Mathematica here and actually go ahead and do this, right? Go ahead and say eigenvalues, and you pass it C1R of psi, right? Just pass it that 3x3 matrix here, right? And see what this spits out, right? So let's call this, I don't know, vowels, right? If you do this here, Mathematica is going to say, okay, the eigenvalues of this thing are, you get a lambda 1 here of 1, a lambda 2 here of cosine psi plus sine psi times I, the imaginary number, and then lambda 3 here, since it's 3x3, you better have 3 eigenvalues here, right? So this is cosine of psi plus sine, or sorry, this should have been minus. It doesn't matter which order. One of them is minus, one of them is plus. Here, right? So you quickly see by inspection here, yeah, magnitude 1. This thing here is, yeah, magnitude 1, right? Because here's the real part, here's the imaginary part. If I square this, add it to the square of this, square root the thing, I get a 1, right? Cosine squared plus sine squared is 1. Same thing down here. So all magnitudes are 1. So great, that passes our idiot check here. So I think that's very refreshing here, right? Okay, great. Tell you what, let's look at an example of applying this. How about? So let's see here. Yeah, sure. Let's erase all this. I think we don't need any of this any longer, and we'll consider an example here of. Again, I'm an aerospace engineer, so I like to look at aircraft. So let's look at trying to describe like the wingtip of an airplane or something like that. So let's look at a very simple example here. Okay, so let's call this thing describing a wingtip location. Okay, so what I want to do here is let's just draw ourselves an airplane here. You know, I'm a horrible artist. You're going to have to excuse me here. Top view of an aircraft here, right? So here's the wing, maybe here's a cockpit, something like that. Let's say the center of mass of the aircraft is somewhere like here, okay? This is a horrible CG picture. Let's do it a little bit better. Okay, there's a CG of the aircraft, okay? So what I can do here is let's go ahead and attach a reference frame to this aircraft. So it's very common to have what's called the body frame attached to the aircraft. So the origin here is at the center of mass of the aircraft. The x-axis comes out the nose here. So let's call this x hat body, right? The y-axis comes out the right wingtip, or close to the right wingtip here. Y hat body here. You know, if the wing is swept like this, you see it doesn't really exactly nail the wingtip, but you get the rough idea, right? And the z-axis goes creates a right-handed system with this. So in this case, it goes through the floor here, right? So z hat body goes into the floor, right? Something like that, right? Okay, so that's a body frame. Now let's think about what we might want to do here is, what if I wanted to describe the location of the right wingtip here, right? So, or maybe tell you what, let me draw a point here, like maybe not exactly the right wingtip. How about this point right here on the wing here, right? So again, we can draw this in a red vector here. It kind of looks like this, and there's probably some component in or out of the board, right? Because the aircraft probably has, you know, probably has dihedral or anhedral or something like that. So the wings are probably tilted up or down to some component here, right? So let's call this vector here. This vector is R wingtip, okay? So what we might want to do now here is, can I describe this vector here, right? So I want to numerically write down, how do I go from the origin here, the center mass of the aircraft, to get to this wingtip? Well, it's very easily expressed here in the body frame here, right? So what I mean by that is, okay, I've got this vector here, but if I want to write down and express this in the body frame, I could say here now, I need just 3 numbers. So this number, the first number, is how far do you walk again in the x hat body direction to get to the tip. The y, the second component is how far do you go in the y, and the third component is how far you go in the z, in the body frame here. So in this case, you might see, okay, x is 0 here, right? Because it's exactly aligned with sort of this y-axis. And then the y-axis, I don't know, let's make up some number. How about, you know, 1.76 meters or something like that is the semi-span of the aircraft here. And then the z-axis is, yeah, maybe there's some component here. I don't know, let's make it up, 0.12. So I guess in this case, we're saying the aircraft has a little bit of anhedral, so the wingtips are a little bit kind of downward canted, like such, because you apparently have to walk, you know, 0.12 meters down or into the page in order to get to the wingtip, right? So great, this is perfect. This describes where that wingtip is, but it's relative to this body frame, right? Now, let's attach a second coordinate frame to this here. So let's say north is this direction here, right? So here's north, and here is east. And then down is, yeah, I guess the third axis of this northeast down coordinate system is just into the page here, right? So this is this down here, right? So let's make the second frame the northeast down frame. So this here is the x-axis in the northeast down frame. This is the y-axis in the northeast down frame. And this is the z-axis in the northeast down frame, which is shared with the body frame. Both of them are pointing down here in this situation. So now what I'd like to do here is, let's say that these things are now canted over and misaligned by this angle psi here, right? So this is the magnitude of the rotation between the body and the northeast down frame here, right? So from last time, from what we just derived, right, we showed that, okay, the rotation matrix here, we got to be real careful what we did earlier, right? Earlier we got the rotation matrix from the northeast down frame to the body frame over angle psi here, right? This was given by cosine psi, sine psi 0, minus sine psi, cosine psi 0, 0, 0, 1. here, right? So this is the rotation matrix we had earlier. Now what I want to do here is I want to describe this wingtip here, but how many meters north and how many meters east and how many meters down do I have to go? So I want to express this in the northeast down frame here. So what I want here is I want the position vector of this wingtip here, right? But I want to express this in the northeast down frame here, right? Okay, well, we see that, all right, I have the position vector of the wingtip expressed in the body frame here. Now, this is where we see that our indices are going to save our bacon here, right? You might be tempted to just say, okay, why don't I take this matrix here and jam it in here? So this is CB with respect to northeast down psi, right? And multiply those two things together. But you're going to get the exact wrong answer in this case, right? Because we see this subscript does not match this superscript here, right? So these don't match. So clearly what I need to do is I need to flip these indices here, right? So we can use the property we talked about earlier that flipping the indices is actually the same thing as taking the inverse, or for our orthogonal matrix, it's just taking the transpose here, right? So this is really the operation I have to do here, right, in order to make all of this work out, right? Okay, so great. If you basically plug that in, and I think let's use a numerical example just for giggles here. Let's use a psi of 45 degrees here. So let's assume that psi is 45 degrees here. All right, so all you got to do here is run over to Mathematica and plug all this in. So what you end up with here is what? We got our wingtip in the northeast down frame. So let's do this first thing here. So this, I need to take this thing, I need to take its transpose here. So what we end up with here is I end up with a matrix here where it's cosine of 45 degrees. How do I want to do this? 45 times, how about pi over 180? Let's do it like that here, right? Let me maybe make this a little bit bigger. Okay, so this is this 3 by 3 is this is what I want here, right? Okay, cosine. Now this is actually what? It's minus sine of 45 times pi over 180, right? And a 0. So because I'm taking the transpose. Okay, and then I got sine of 45 times pi over 180, and then cosine of 45 times pi over 180. And then 0, 0, 0, 1, and then I multiply this thing by the vector here expressed in the body frame, right? Multiplied by 0, 1.76 and 0.12. Great. Okay, so again, this matrix here is C from the body to the northeast down over the angle 45 times pi over 180. Right? That's what this matrix is. So again, here's again probably the number one place that you're going to screw things up or get tripped up with these rotation matrices is dealing with these transposes, dealing with these indices. Where is the minus sign here in all of these here? Minus sign, S-I-N, right? So that's a weird double whatever like vocabulary thing, right? I'm talking about the sine, S-I-G-N, of the sine of the S-I-N. Well, anyway, you get what I'm saying. Just be real careful about these indices. If you use this subscript and this notation where we make sure that these indices match, so this B matches with this vector that's expressed in the B, and it yields me a vector expressed in the NED, I think everything should be fine. So you do all this math, you run over to Mathematica, you plug in the numbers here, and you end up with, what does this come out to be? It's something like minus 1.244, 1.244, and 0.12, something like that. So here's the wingtip in the northeast down frame here, right? And the interesting thing to note here is only the x and the y components change, right? The z component doesn't change because, like we talked about, the z axes are the exact same in this situation here, right? So here's how you would describe that wingtip here if you were in the northeast down direction. So you actually go this many units north, so it looks like actually you go south. You go south by 1.2 meters, you go east by 1.2 meters, and you go down by 0.12 meters to get there here. All right. Okay, so I think this is pretty much where we like to end it. The thing I'd like to note here is just make a note here and remember here, we did all of this derivation for rotation about the z-axis, right? So we looked at deriving a rotation matrix where the two frames were separated by a common z, were rotated about a common z-axis, right? You could go through this entire derivation here using a common x-axis or a common y-axis. The analysis is virtually identical. All that is going to change is the structure of this rotation matrix. This one is going to move to different locations here, and the cosine and sines will be spread out around here. But otherwise, the format is going to be the same. It's just going to be a whole bunch of cosine, sines, and ones and zeros here in your rotation matrix, and you just need to be careful of where the negative sign, the negative sign here shows up here. And we're actually going to be taking a look at this a little bit later on down the road, where we see how can I actually combine multiple rotations here successively, one after the other here, about both the x, y, and z axes in order to move forward here when we look at Euler angles for an aircraft here. So I think that's where we want to leave it here. I think this is a good spot to stop here. So again, I hope you enjoyed the video here. Please stick with us, because this is actually one of a large series of discussions here on kinematics and rigid body dynamics here, where we're going to be looking at position and acceleration, position, velocity, and acceleration in rotating reference frame in the context of developing a rigid body simulation for an aircraft here. So if you like the video, please subscribe to the channel. It really does help me continue producing these videos here. And leave a comment here. I'd like to see what you guys think here, if there are things that could be improved in the future. So with that being said, I hope to catch you at one of these future videos. Bye.